Hey everyone, I'm Ib Green. If you don't know me, engineer at Foursquare, and have been working on WebGPU since day one. So I think it's over eight years now, and obviously incredibly rewarding to see this strong community we built and keep meeting you year after year and working with you and connecting with you. I have a talk here about luma.gl and a little bit about an overview of that. And I have some slides, some points, about different things. It's not like something comprehensive, and I'm very happy to make it interactive. What I'm hoping to convey is an understanding of luma.gl, why it's, what it is, and some of the things we're working on right now. But I don't want to kind of lose you guys by moving into technicalities around like WebGPU, so on. So feel free to interact with me. And Luma is the GPU rendering engine that powers WebGPU. And so in this kind of framework suite, we initially made the choice. We wanted our own GPU engine. We didn't want to reuse an existing 3D framework. I think there's even a talk about that, comparing us with major like 3JS. But it's a choice we made, and it obviously allows us to control the entire stack. For a long time, this started out as a WebGL 1 framework, luma.gl, and then it became WebGL 2. It became a WebGL 2 framework, and it was very centered around exposing the capabilities of WebGL, which, if you worked with it directly, is a pretty horrific API. It's like a 25-year-old function-based interface with weird ways. So if you have to pass parameters by binding them and this and that. So it made a lot of sense to have a wrapper around it that made it easy to work with. And so as we moved to WebGPU, then the idea was always that we wanted to be close to the GPU. We wanted to write code that was similar. If you knew the WebGL API, you should know luma.gl, and if you learned luma.gl, you should basically learn GPU programming WebGL at the same time. So those principles still exist today. But when WebGPU came around and we looked at that API, we said, instead of maintaining the old API and that was kind of a WebGL style API and try to implement that on WebGPU, we said, let's make a fresh start. Let's create a new API that is close to WebGPU, because that's the future for GPU on the web. And then let's make a WebGL implementation of that. And so that's a little bit of background. I'll talk about different topics here. So, and I think this is something that we already mentioned before, and it's going to be talked about in more detail, I think, by Felix and maybe others. So WebGPU was not designed by its designers to make porting from WebGL to WebGPU easy. You could almost argue that the very opposite is true, and so I call it knockdown blows. Like WebGPU, like several things that require a tremendous amount of effort and change to the structure of WebGL, and one of these may be, not really the fault of WebGPU, but uniform buffers is the efficient and right way to provide. So if you don't know what uniforms are, they're basically when you start a shader, you need to communicate some information to it, some variables from JavaScript in our case into the shader code, into the GPU. And one of the ways of doing that is uniforms. Think about it as constants, that constant values that you can declare in your shader, and you can set them in JavaScript. They can be things like can be properties from a layer, the scale at which you're rendering things, or the projection matrix calculated from your views and all of that, right? So there's quite a few uniforms in play, 50 plus per layer. And so previously you could just set them in the WebGL API. Set them, just set uniform, and you could say, I want to set this uniform. You gave it the name, same name as the shader, and you could set it to a value. So it's quite easy, but very inefficient. But in UBOs, you have to basically you declare a struct in the shader. Then you have to lay out a buffer. You have to put all the values from JavaScript, exact byte alignment as is expected of the shader. So you need to know this, layout on the GPU, and then you need to map all your JavaScript values into like a binary layout. So, and on top of that, have multiple uniform buffers. So different modules, different layers, and so on. They all, we have all these shader modules, and so each shader module has its own uniform buffer. And so now you're managing a bunch of different uniform buffers, and you have to all set them, and you have to route the right shader values to the right uniform buffer, and so on. So this has been an absolutely massive effort. And in 9.0, we introduced obviously the support for uniform buffers and implemented it on WebGL and WebGPU. It's supported through the API. There's the render pipeline, and then we have the more powerful model class that supports it. We created a new shader inputs class to deal with it. We have these uniform layout classes that help us, do the precise layouting and so on. And if that wasn't enough work, then we had to migrate all our shader modules use on uniform buffers. So they all had to be updated. All the syntax in the shader modules had to be changed. And then, it's literally hundreds of GLSL shaders. All the, not even going into the new shading language, existing shaders had to be created. And then obviously in JavaScript, you had to now use the shader inputs and other things. So that I'm very, very happy to say is done. So, within a couple of weeks, hopefully we have released 9.1, no code that uses classic uniforms, but uniform buffers. And yeah, you can see down here, it's just a very short, previously you could just set your uniform like this. Now you have to create the buffer, populate it in a very exactly precise way, and then you set a binding to that uniform buffer. But on the upside, it's now very easy. Once you've set this binding, you can update this uniform buffer. You don't have to rebind it. You don't have to reset uniforms. And so it's a much more performant API. We'll come back to that. I mean, the other big knockdown blow, I'd say, from the WebGPU team, and this one is a little bit harder to not assign some fault, is that they decided to create a new shading language. And so instead of building on GLSL, and maybe, WebGL2 was using GSL 3, maybe GLSL 4, or at least have support for that, they decided to create a completely new language. And, based on, I would call it Rust syntax, which I guess is very fashionable. And this means that all our shader code basically doesn't work. And we had looked at different strategies, and I think this question comes up every now and then indirectly. So one on the I see several frameworks taking is that they double down on GLSL, and then they find look for tools to transpile it automatically to WGSL. There was a tool called GLSlang that was a compiler. There's Naga, I believe. So on. A little bit of work on those, but they did not convince me. GLSlang didn't seem to be going anywhere, and it really felt like the spirit of luma.gl, is to adopt the latest and greatest ways of doing it. Why limit ourselves to the old way, GLSL way? And so the current strategy right now is that we write double in. So every shader module, every layer, and so on, a GLSL shader and a WGSL shader. It's extra work, but at least it means we'll all build our WGSL skills, right? So we all as contributors need to really understand all the opportunities and limitations and so on of the new shading language. A dream is to be able to standardize on WGSL and find a solution to then transpile it automatically GLSL on WebGL. But we need tooling for that, and there are discussions. I see things, maybe some things emerging, maybe there's already something available, but it's it's a work to integrate it and figure everything out. So maybe we come back next year and can tell you that we've dropped all our cell shaders then. Very great. And again, this is interactive. If you have questions on these things, like
So is this library in any way tied to DeckGL, or can anyone use it to
so luma.gl, so we build all our libraries in this suite as independent composable pieces. So each library is broken down into submodules. So we have luma.gl core, and then luma.gl engine, WebGL, like a bunch of different modules that you compose as you need. DeckGL is the same way. We have a math library, we have loaders library, and they're all independent, but they are also designed to work really, really seamlessly with each other. So you could
transition MapLibre GLGS to WebGPU with this library.
Absolutely. But I think the biggest obstacle there is probably that MapLibre wants to also have a native strategy, and this is a web only.
No, but I was talking about GLGS, so the web version of MapLibre.
Right.
Yeah, if you look at the repository, then we have a bunch of examples which actually show an application that's built purely in Luma, from like simple stuff like drawing a triangle or a cube, but also loading like GLTF and doing lighting, like something that is actually beginning to look like an application. So it's not like luma.gl is tightly coupled to DeckGL. You can actually do quite a lot of things just alone with luma.gl.
I mean, if you wanted to go with a JavaScript solution in MapLibre, if you didn't want to, say, create a common WebGPU implementation in Rust or something, and then you WASM compile that into your JavaScript version, then Luma is not a bad choice, because it's a tremendous amount of work in creating this, portable layer. So, if there's any interest, I'm happy to join the conversation.
I doubt it would be. I doubt it is a viable, I suppose, a hypothetical form strategy. A third language, it piles down to GLSL or WGSL.
Yeah, I missed that one. That's and I kind of joke a little bit about it, because every time I see a 3D framework, right? There's some in WebGL, but there's some JavaScript. There's many native C and C++ and so on. In the end, it always seems to be an irresistible temptation for those framework maintainers to create their own shading language.
That will come up in my talk in a few
minutes. If they just made more of a kind of bytecode type thing, the WebGPU, rather than a shading language, which is sort of
there's some depth to that. There is something called I don't know how to pronounce this, SPIRV or SPIRV, but it's basically a binary representation of shaders, and it's supported by Vulkan and maybe others. And I think there was a lot of discussion initially that WebGPU would accept these binary shaders, and you could create them in any way. You could file them from LSL or whatever. I think WGSL is probably designed to be like a one-to-one mapping to SPIRV, but as far as I'm aware, there's no support in WebGPU for. You probably know.
Not on the web. Yeah.
It does at least mean that any tooling that exists around SPIRV, you can be fairly confident that it will sort of work.
Yeah.
Anyway.
So yeah, and I think that still the philosophy of Luma is to kind of align around the modern way of doing things. So I think we would rather align on WGSL code rather than create our own abstraction layer that you have to learn that's not portable to others. But I think there's also been some interesting discussion with some other communities recently. There is this idea of creating a set of extensions or keywords or whatever on top of WGSL that solve some of the problems. Instead of inventing a new language, it's a little bit augmented, and you'd run it through a preprocessor that would give you some module import systems and solve some of the other issues that I'm working on. Here's the slide. We can come back to that, but yeah, some kind of augmentations on WGSL will probably be needed. But right now, I'm not convinced that we want to go with inventing our own language.
Opinion. I feel that there's always things you can do that's like very clever and has a ton of stacks of dependencies, but ends up with a very small code base, very small bundle size. But then when there is a problem in there, it does become part of the problem, and nobody can look at your source code and understand what's going on. And WebGL is already intimidating enough for a lot of people, but we do sometimes have external casual users or first-time users come in, they have a rendering problem. They look at the shader and they understand what's going on, and they open an issue and talk about it. If it's some obscure language that we come up ourselves, nobody is able to do that.
If you were learning something new, if you had to go to DeckGL, would you rather learn WebGPU, which is reusable, or would you want to learn some weird abstractions that we've created? I think it's more a big. It's a good question. Right, so we've already talking about how we're porting the shaders.
Might be a dumb question, but you're talking about Luma as kind of a, I don't know, a wrapping around WebGL, WebGPU, right? So I'm not sure I understand the conversion of shaders as part of Luma.
They decided not to do that and just
have so yeah, I can give you some. So Luma has a pretty extensive. So Luma has a shader module system that allows us to create reusable pieces. So there is no import statements either in GLSL or WGSL. So we have a lightweight shader module system, and so we provide a big library of shaders, lighting. We have like different lighting modules. I mean, the biggest one is probably the PBR, physically based rendering, for GLTF models. We have projection modules. We have a big set of post-processing effects, so you can apply different types of post-processing techniques. So there's a ton of shaders in Luma. And then, of course, there's even more shaders in DEC. For each layer has its pair of shaders, and there's all the extensions that have shaders and so on. So overall, between Luma and DEC, we have hundreds of shaders. And so, transitioning all those shaders, which in this current strategy means creating a WGSL version of the shaders for every shader module, every layer, and so on. That's when we talk about, porting shaders.
Yeah, I was. I think I'm probably referring to a much more smaller piece of Luma that actually provide the basic APIs around WebGL, WebGPU. That might be interesting.
Yeah, so Luma has a structure. There's a core module that contains this portability layer, and we're trying to make that as minimal as possible so that it's as easy and clean as possible, easily to debug and maintain, like the WebGL and WebGPU adapter modules. But then there's modules built on top of that just uses the core API and then become portable. We have a big engine module that contains things like animation loop, the model that brings together all the capabilities and other classes that I will mention. That makes it easier to work with. So Luma is, at its core, it's this portability layer, but it contains a lot more. Give some context. I'm not going to go in too much into this, but there are issues with WGSL. On one hand, it has more structure, but that structure is also a problem. So in GLSL, there's something called attributes and varyings, which is a way to get your table data attributes, you get your table data into the shader, your columns, you declare your columns, binary columns, and varyings is a way to communicate between the vertex shader and the fragment shader stage. In GLSL, these are just like global statements that you add. So it's very easy in a shader module to just add, an attribute or a varying. But in WGSL, these have to be parts of some structures. We by convention call them vertexes. And so now instead of just adding a line of code somewhere, injecting a line of code, you have to create code that goes in and splices these new things into the structures. And so there's a lot more surgery required on WGSL shader code to implement, a strong module system. And so the strategy is still in development. And I mentioned this idea of an annotation system for WGSL. Another thing, if you've been doing advanced work with shaders in DeckGL, we support a shader injection system. So you can basically identify different points in the WGSL shader, in a GLSL shader, and add your own custom code. So if you want to customize a really complex layer, like the path layer shader, you don't have to copy the entire thing and then have it go out of date. You can just inject a little bit. This is much, obviously GLSL injections are not going to be portable to WGSL, and we have to figure out if we even want to support it in WGSL. So that's a heads up. Okay, I don't have so much time. Another random topic, immutable. So in WebGPU, things are immutable. We had in Luma V8, we had created a lot of convenience features in the classes. So buffers, textures, frame buffers, had a lot of features like you could resize them, you could do asynchronous stuff with them and so on. And so this made it really hard. The code base was really complicated, it was really hard. So what we're doing in the V9 series is we're making these core concepts really simple. So textures now will no longer support resize, no longer accept promises for data. They won't automatically calculate their size. They won't automatically generate maps and so on. Massively simplifies our implementation, but obviously creates problems for applications. And so in this engine layer, we're building a new class, async textures. Makes textures mutable again, if you will. It brings back the capabilities of the dynamic capabilities. And so under the hood, you have a very immutable, efficient, easy to maintain texture. And then we have all of these texture resizing, map generation, loading, and so on, separated out in a layer on top of that. And that's already happened, buffers and so on. Obviously, WebGPU has a bunch of cool new features. So there's texture views. So in WebGPU, you can have a single texture. Texture is a crazily complex object. It has not just one grid of data. It can have like multiple MIP levels, and then you can have an array of textures. So you can have an array of arrays of images of different sizes. And in WebGPU, you can specify a view. You can take just one of these depth layers or one of these MIP levels and specify one view, and then you can create another view of something else, and then pass that to shaders. So it gives a lot of flexibility in how to work with textures, and that's now exposed in the API, and we use some of the parameters in WebGL to make that part of that available and kind of emulated in WebGL. You can have separate sampler objects. So in WebGL, you know, all the sampling parameters are typically stored on the texture. But now you can create multiple samplers, pass them to your shader, and you can sample the same texture in different ways. Single shader. A big effort is also portable texture format support. Texture formats are quite complicated. And obviously, in WebGPU, we have these nice string constants. In WebGL, it's all these numeric constants. Then you need to discover whether there can be different capabilities. Can you even create them, or can you render them as from a shader? Can you write into that? Can you sample it? Can you render it? Can you filter it? Can you do sampler filtering? Can you blend into that format? Can you use it in storage buffers? We have an API now that allows you to discover what capabilities you have on your platform, use the WebGPU style string constants, and figure everything out easily. Now, I think this comes back to the question from one of you earlier on about performance. So I hope I have a few extra minutes. So I think this is kind of the reality check. So you often hear on forums and so on that porting from WebGL to the more modern WebGPU will automatically improve performance, and people throw out numbers, from 2x to 10x to 100x and so on. And then you'll find occasionally, people who object very strongly to this, and basically saying that, just a new API, the underlying GPU hasn't changed, right? So really just accessing the same things from a new API. New API doesn't make it faster, the GPU faster. And then obviously the OpenGL stack has been around for decades and optimized, and WebGPU is still maturing. Those are some of the main things, right? So with that said, right, that's just a reality check. We're not just magically going to get get improvements. But we talked about uniform buffers. So what we've seen in applications with a lot of DECGL layers, like especially you may know that many DECGL layers are composite. So when you render them, they actually render other layers, use other combination of other layers, underneath to actually do like a GeoJSON layer renders a scatter plot layer and a path layer and a polygon layer. The tile layer renders GeoJSON layers that then renders all of these. So even if you only have like a couple of dozen of layers, you may actually have layers underneath. And each layer may issue 50 or more set uniform code, V8. So you can run into 5,000, 10,000 set uniform calls. And these are WebGL API calls, validated. WebGL revalidates and revalidates for security purposes your inputs every time. And we've seen this take 10 to 15% of the frame render time. And so this move to uniform buffers should reduce, especially on the CPU side, the overhead for any application that uses a lot of layers, right? It should be at 10, 15%. We haven't actually measured, we haven't started benchmarking, but based on numbers we've seen before. So that's a really, really nice benefit. Obviously not a saving on the GPU, but on the CPU, all the preparation work. Then we can look at other things, right? In WebGPU, all the objects are immutable, right? We talked about how we needed to simplify the API to handle that. But the beauty of that is that there is so much less API validation overhead. You create them once, and then WebGPU knows that once it's validated, that object is good. And so this is maybe one of the magical things you get with WebGPU. Again, this is validation happens on the CPU, and so here maybe we have another 10+%. So maybe we're up at 25%. CPU. One of the biggest things we suffer is buffer texture readback. Whenever we want to we do all these beautiful things on the GPU, we do compute with transform feedback, and we do perhaps into textures with picking and so on. But then we need to get the data back to the CPU. In WebGL, this is synchronous. So we get this catastrophic GPU stalls. The entire GPU pipeline needs to run out. And the GPU tends to queue commands and run them asynchronously, right? You fire off these commands from JavaScript, and then they happen asynchronously in the GPU. But here, like, we have to drain that command pipeline, and this causes tremendous performance issues. And in WebGL, we finally get async readback. So yeah, it still takes some time, but the GPU doesn't stall, the CPU doesn't sit and wait, and we get the promise back, and when it resolves, we have the results. So this is just a major thing for. We talked about compute shaders. They do require a lot of tuning to get good performance. So it's not just writing the compute shader. We have to optimize workgroup sizes and other things. They will definitely outperform transform feedback. And then we talked about some of the other things in direct draws that can avoid GPU, CPU, GPU round trips, storage buffers. More algorithms can be moved to the GPU. So I'm not going into this other than saying that there's something in WebGL as well. We now support sync shader, compile, and link. Shader linking in particular can be very slow in WebGL, and again, stalling the application for 2 seconds while a big shader links can now be avoided. We haven't enabled it in DEC yet, but support is there. It's also nice. A lot of attention also on debugging. So debugging GPU is quite tricky because you write your shaders, you file them off, and often once, like, initially you get some compiler errors in the shader and you want to get through those quickly. We have support for that. We have beautiful shader error logs that pop up in your canvas, and it makes it really quick to iterate on shaders and sort out the errors. But then you get a black screen, something's wrong. And so you really want to have these capabilities, right? Like, you can't put any breakpoints in a shader. So we have like the general debug flag that synchronizes errors. So you get, it throws an error right in the WebGL call where it fails, and normally that's asynchronous, and so you get an error after a while and you have no idea what went wrong. We have frame buffer debug, so you can, if you're writing into frame buffers, compositing off screen before, and then you don't see anything on the screen. Well, which compositing stage did it go wrong in? Well, you can now display the frame buffer content as mini images in your canvas. You can see, those compositing stages are, you can see where things go wrong. And debug flags can be set on device creation. So Luma create device, there's a bunch of debug options. And you can also set them in the console. So if you're familiar with that system, you can all enable, you have an application running, you can just go in and turn on the debug flags and continue working in the browser console. Not have to go and change your source code.
Can this part of the code be tree-shaked? Debugging stuff?
If you look at these two later points, so the two big pieces of code here is that we use the WebGL Chronos debug tools to, intercept, hook into the WebGL calls. That's quite a big library. Now we dynamically load that, so there's no bundle size penalty. When you activate this WebGL debug, that code is dynamically loaded into your application. And the same, we also have a strong Spectre.js integration. Now Spectre.js is a beautiful, it provides a beautiful UI that allows you to really see what's going on with the WebGL calls and your frame buffers and all the parameters and all that. That's also dynamically loaded. So when you turn on Spectre.js, you also the rest is part of the code. So,
Is Spectre.js is going to be supported with WebGPU as well?
I haven't heard any indications that it will be.
It's indeed very useful debugging.
So at least we have it on WebGL, and if they do something on, they're able to do something on WebGPU, we can. I don't know that WebGPU has the right hook, maybe. For WebGPU, we've added, there's a validation API. So we're now starting to add that and wrap things in this validation API, and which means that we're now routing those devices to, if you provide an on error in your device, when you create your device, you can actually hook into all of those error messages dump into the console. And you get a little bit more control. You can break in the function where it happens and so on. And there's something else in WebGPU, which is called error scopes. So you can basically tell WebGPU that right now we're starting the render pass for this application. Then you can say, oh, right now we're rendering this model. So it becomes a stack. You can say, now we stopped rendering this model, now we're rendering this. And when you get the WebGPU error, you get a stack of these. You can say, okay, so this error, blah, 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 happened during the application's render pass, or picking pass, and it happened during the render of this model while setting the bindings or whatever. So it's really, really helpful because it can be overwhelming to just get a random WebGPU error, and now you see the logical context, and so and that even applications can opt into that and kind of add on to that stack.